Okay. How are you doing, everyone? And I hope you are good and you are doing well. So I've got some time, so I'm going to share something a little bit quick. And mainly it comes to what we call polygenic inheritance. And as usual, you know that whenever I have time, so I try at least to share things from genetics. And even I think as time goes, I'm going to share things on other topics, including reproduction. And I think the other things that will come from coordination and everything. So everything will be interesting here. So make sure that you put comment if you have any suggestion from what I'm doing here, and if you have maybe any question you can put there, and when I have time I'm going to answer it through the comment section, or sometimes you can maybe send message through those numbers that are listed in video descriptions and also in a channel biography. So welcome to the presentation on what I call polygenic inheritance. So today I want at least to share something from polygenic inheritance because I know one of the pattern that is too much confusing, and none of the book that I have ever touched have already talked clearly about that is polygenic inheritance. I think you know all the common books that are used in secondary schools, always they miss those important information from what we call polygenic inheritance. So at least my book has said a lot about that. My book, you see. Polygenic inheritance, and I wanted to type something, yes, this one, you see, Mastering Genetics. Now this is my book. So this book, always I call it as Mastering Genetics because it has touched almost all those key things that are needed to be known by students in high schools, and specifically in Tanzania and even East Africa, because there are certain things that are shared. So Mastering Genetics is the first book in genetics that's going to provide you with all the basic informations. So straightforward, let us see polygenic inheritance. Maybe let us see polygenic inheritance. Let me take that. So let us see polygenic inheritance. So basically this is just a highlight on what is polygenic inheritance. It's just part of the book. So if you need to read everything from my book, just make sure that you have a copy of that book. And I have copies of other books, but my genetics book is not there. My genetics book is not there. From all the copies that I have, you see, I have this. I have this for cytology. And I think you know this copy. And also I have got the other one. I have got this for practicals. I have this for practicals. Now, but for genetics, I don't have a physical copy. Because everyone want it. So even the stock is out now. So we can wait maybe for some time to have a copy for now, a printed book for it. So basically, polygenic inheritance now is among the non-Mendelian inheritance patterns. Now, always non-Mendelian inheritance patterns, they are of different types, and I think in one of my video I already listed those non-Mendelian patterns. So polygenic inheritance is among of them. So in polygenic, we call it as polygenic because it's a pattern of inheritance that include many genes, polygenes. So when you say something is polygenes, it means many genes are included in influencing the single phenotype. So if there is many genes influencing the single phenotype, so it deviates from the Mendelian concept, whereby Mendel said that actually each characteristic has got a single gene that influences it. But when it comes to polygenic, it's just more than one gene influence a single phenotype. So the most common examples will have those characteristics that show continuous variations. Things like skin color, things like eye color, they are most common in animals, always showing polygenic inheritance. So basically, in polygenic inheritance, what is important is now those characteristics. I mean those alleles now of those genes will show what we call the additive effect. So what is important is to understand the additive effect. So what is additive effect? Actually, when we're talking about additive effect, is when the effect of one allele plus another allele is just the product of summation of those who call the two alleles. So I don't know if you are getting me, but maybe as I go on, you'll understand, and specifically I'll give a real example of what is additive effect is going on. So now basically, we can consider the case of inheritance of kinyl color, that is the endosperm part of wheat. So basically, in the case of kinyl color in wheat, we can have two genes that control that particular color. So we assume them being gene A, gene B, and gene C. Now those are the genes that control kinyl color in wheat. So having those genes, remember in polygenic inheritance we don't have those dominant and recessive effect. So what is important there is just additive effect. So and that additive effect is brought by those who call the uppercase alleles. So we'll have those alleles that maybe specifically in the kinyl color. We will have those alleles that produce pigments, and then we will have alleles that do not produce pigments. So what happens now? Uppercase alleles, we can have maybe this one maybe for ABC. They will produce pigments, and then we have the lowercase alleles like this, maybe the small a, small b, and the small c. They will not be producing any pigments. So you'll find that maybe in kinyl color, those uppercase, they produce a reddish pigment. So when we have caps A, it means we will have small amount of reddish pigment. When we have maybe we have caps B together with the caps A, it means the amount of pigments produced will be increased. So that's the idea of additive effect. So in a simple way, additive effect is summarized like this, maybe with this statement. Now this statement is summarized what is additive effect. Additive effect is when a combined effect of alleles is equal to the sum of their individual effect. I think this is the only way to maybe clearly explain additive effect is when the combined effect of maybe particular genes or alleles is equal to the sum of individual effects. So let us see clearly an example in relation to kinyl color. So for example, when you have those lowercase alleles now for that gene A, B, and C, you'll find that none of the allele there produce pigments. So if none of the allele produce pigments, it means now we're not going to have those who call the reddish pigment, because the case there is reddish pigment. So if we are not going to have reddish pigment there, it means now the color is not going to be red at any degrees. So now the color is going to be white. If we don't have any reddish pigment producing allele. But now let's see now in this case now, when we have at least a single pigment producing allele. So we have this caps A there. Now caps A produce pigments, produce reddish pigments. So we have, if we at least have that single A maybe, or we have at least a single B, or we have at least a single C, now the single caps C, it is when we will have small amount of reddish pigments. So the case there is the effect of caps A, the effect of caps B, and caps C actually is the same. So this first genotype, the second genotype, and the third genotype will have similar phenotypic effect. So now from there we'll find that the color will be very light. Now the color is transforming now from white to very light. So you find that we have started having degrees of phenotypes now. We have started having degrees of phenotypes. So those degrees of phenotypes is we are from white when there were no pigment producing allele, and now we are to a very light when we have at least one pigment producing allele, and now when we have two, now what happens? Do you see those genotypes there now? So from those genotypes that we have there, we have at least two. Now we have two pigment producing alleles. So now the first genotype, the second genotype, the third and the fourth, always they will produce similar degree, and actually the intensity of the color is going to be deep compared to these genotypes there that had just a single pigment producing allele. So here we are going to have a light red kinyl color. So just from a very light, now it's turning red now, we have a light red kinyl color. So now things will go on, the degree increasing now, the degree is going to increase as you increase the number of pigment producing alleles. So now the concept there is going to be like, maybe if you have this A, B, B, C, C, and then you have A, B, B, C, C. So now this will be genotype for individual with a deep color. So now this will be genotype for individual with a deep color. And then this one will be a genotype for the one that is missing that particular color. So it's going to be like, so you'll find that now when you have everything is capped, the color is going to be dark. Now this color is going to be dark. Now those reddish pigments now will be accumulated to an extent that they are turning that color into dark. So I'm sure now you are getting something about what is additive effect. And basically this is the one that is going to govern the polygenic inheritance. And now when we already have that, the basic concept now is just to understand, the basic concept is to understand now exactly how we are going to have a crossing. And I think the only problem with the students is now managing a cross that involve more than two, it is just now more than 2 genes, and specifically we have those gene A, gene B, now we have plus this one. So it is more than 2 genes, and specifically it is more than 4 alleles. So here we have 6 alleles. So when it comes to 6 alleles now, most of books even have not presented how you can formulate gametes and everything. So most people fail on how you are going to do that. So we have got different ways, but one of the most preferred ways, and I have presented it in my book, I use a fork line method. So how you are going to work with the fork line? So basically, on those crosses that we do in dihybrid, when we have 4 alleles, I think you know, when we have 4 alleles, what we do always is just showing those we call the independent assortment. The idea is this one has got a chance of combining with this, and at the same time has got the chance of combining with the C. So our gamete will be A, B, C. We will have this, the first gamete. Then this one, when it's together with this caps B, has a chance of combining with the second one. So also this will be A, B, C. Now at the same time, now the first with the second, now we'll combine with the first. So we'll have the same thing. So basically doing this now with the second one, then we'll do the last one now. So we'll be A, B, C. So these are the possible combinations of this A with the rest. Then we'll have the second A now, this one. So we'll have the second A, we'll have similar chances with the first one, with the third one. So you'll find that now everything's going dead there. Everything's getting dead. So if you are going to use this method, everything's getting dead and nothing's going to be clear there. So what you're supposed to do is just, we'll have to use alternatives now. So we'll have a fork line method that I have presented in my book. So always I recommend you to write something like, so you like there is, now you have those 2 things there. We'll have AA, but if you have everything caps there, probably will not understand exactly what's going on. So let me change some letters there. So I assume that those individuals, they are heterozygous. So if they are heterozygous, we'll have small a there, we'll have small b there, then small c there. So now you'll put caps A and then small a down there. So now this small a have a chance of combining with caps B, at the same time have a chance of combining with the small b. Now when this one is with this one, has got the last chance, may combine with caps C and also may combine with the small c. Now the same thing, this one with the small a with the small have a chance of combining with caps C, also with the small c. So in fact that our gamete, our first gamete here will be A, B, C. This is our first gamete. Then the second gamete will be A, B, small c. So now things goes on, we'll have A, B, then caps C. Now the last one is just A, small b, small c. So these are the gametes from this caps A. Small a will do the same thing now. We'll have a chance of combining with the caps B. Then things goes on with the C. So I think you have got the concept. So what I'm doing here is just giving you the concept. So you will do that, and then you will have 8 gametes. So having those 8 gametes, when you draw the Punnett square now, it's going to have 8 gametes for male, 8 for female, so 64 possible combinations. So this is the only way people fail.